Good morning, everybody. So it's my big pleasure to introduce David Valls-Gabaud. So he did his PhD in Cambridge under the supervision by Zaslow. And then he has been a postdoc at the University of Toronto in CETA, Paris, Strasbourg. He got his permanent position in Strasbourg. And he is currently in Paris. He has moved to many places, so he has been working quite internationally, promoting the science he's interested. And in fact, he has a large number of research interests, including gravity, stars, cosmology, radio astronomy. And in the last year, he has been most interested on this topic. He's going to talk about the low sulfur brightness universe, including from galaxies to cosmology, including also some properties of our own galaxy, like the galactic cirrus. So, David.
Okay, thank you very much, Nacho. It's a pleasure to be here at the Institute, where I have so many friends and collaborators. Today I'm going to talk about this mission that we submitted to ESA a couple of years ago. And this is a large number of people interested across the planet, from China to Chile, to Canada, to Switzerland, including the Canary Islands. And so this group of informal group of 120 people or so are interested in the low surface brightness universe. And the context is the following. We know roughly the initial conditions from the lambda CDM model, given that the fluctuations of the CMB. Now, these fluctuations in temperature may arise either from isocurvature fluctuations or from adiabatic modes. And what Planck has shown is that essentially the isocurvature modes are ruled out at the 95%. And so the fluctuations are essentially adiabatic, which means that the fluctuation temperature is going to be proportional to the fluctuations in the density field. This density field is going to evolve through nonlinear evolution and produce nonlinear structures like filaments, clusters, and galaxies. So assuming dark matter, which drives this instability, we understand from the 1000 to the nearby universe. And the success of this model has been so huge that you will be hard-pressed here to know whether those are observations or those are simulations. I'm telling you those are observations and these are simulations. So the success is absolutely amazing, and some people will claim that perhaps we know everything about galaxy formation. Well, perhaps not quite. You can see here two of the phenomena which have been predicted by the lambda CDM scenario, which have not yet been tested. One is the existence of the Cosmic Web of Filaments on scales of hundreds of megaparsecs on a very weakly nonlinear regime, very low densities. And all the way through to the highly nonlinear regime on scales of dozens of kiloparsecs, where the densities are very high. Now, these two regimes, as you know, are the ones which are causing problems to lambda CDM. And yet, in spite of the wide differences in densities and sizes, they share one common property, which is to have extremely low surface brightness. And so I'm going to argue in this talk that we don't have the proper instrumentation to detect the very low surface brightness of the cosmic web, nor the very low surface brightness of these satellites of the galaxies. Now, those are the two driving science cases for this mission. Understand how galaxies form through accretion, the problem of the missing satellites, the mergers, the disk of satellites, and so on. And the second one is, what are the properties of the cosmic web? Do the baryons follow this dark matter? Are they shock-heated? Are they ionized? We don't really know. Now, those are not really new ideas. They have been identified by a number of panels, like ESA, NSF, Astronet, as some of the key questions in cosmology these days. Now, going back to number one, we have seen, thanks to essentially Sloan, the existence of large number of streams. Those are the features of galaxies falling into the potential well of the galaxy. And the question is, we are resolving them into stars, so we cannot really do that beyond the local group. So how many of these streams belong to these past accretion events in other galaxies? This has been one of the successes of Sloan, and you can see that these galaxies were found by small the density contrast around in these fields, and you see galaxies extremely nearby and all sorts of sizes. Now, in spite of this success, the large number of galaxies found by Sloan, we still have an order of magnitude difference with respect to predictions. We may have something like 100 satellites around the Milky Way, whereas predictions rather robustly expect at least something like 1,000. And so this tension is so huge that perhaps we have to change the properties of dark matter. Perhaps it is self-interacting, perhaps it is warm, in which case you are erasing power on small scales. So understanding the abundance of these satellites is a way of understanding the nature of dark matter. Now, before jumping into saying, okay, perhaps dark matter is different, let's look at the observations, because perhaps observations are biased. And this is the number of satellites known of the Milky Way as a function of time, essentially through photographic plates in Schmidt telescopes. Sloan was absolutely instrumental in essentially doubling the number of satellites, and now DECAM has doubled again the number of satellites. And this is a tiny fraction of the sky. It is not yet complete. And we know something like 50 these days. I expect that it will be something like 200, perhaps even 300 across the sky, again through resolved star counts in the nearby halo. So perhaps, when the lambda CDM or CDM was actually predicted in the 80s, we only knew of something like a dozen satellites. And so the tension was even higher. So perhaps just a question of detection bias. Now, the reason for this is that you see one of the satellites of the Milky Way here is huge. It's as large as the full moon. Can you see it? No, of course you can't. You have to do a redshift survey and then realize that all these stars actually belong to the same galaxy. So this galaxy is only at 23 kiloparsecs from the center, and you see it's as huge as the full moon. So if this galaxy were not at 23 kiloparsecs, but a few megaparsecs away, you only see a small blotch of unresolved stars, and you will miss it. Likewise, Crater 2, this is a huge galaxy here. You don't see it? No, for sure. Let me enhance it. That's the galaxy, okay? Larger than the full moon. And again, this is nearby. So how many of these denizens of the halo are still there to be detected? Now, all these galaxies that have been detected so far in the local group, once again, if you look at the magnitude versus size, you see that they start populating the surface brightness between something like 27 and 30-31. So again, if these galaxies were a bit further away, they will not be detected through resolved star counts. Yet, these galaxies are extremely interesting because if you look at the mass-to-light ratio, say as a function of luminosity, all these have mass-to-light ratios of 1,000 or several hundreds. So those are the most dark matter-dominated objects in the universe. So again, not only is it a question of abundances, but also the fact that these galaxies are extremely dark matter-dominated. And they have been found almost everywhere. This one, Leo 1, is well known, but if you go all the way to this is 100 million times fainter than the Milky Way. And again, those are not low luminosities, but large sizes. And again, these will not be detected beyond, because we cannot resolve them. With ELTs, with TMTs, we will be able perhaps to resolve their populations, perhaps to Virgo, but not beyond. So, in spite of the huge success from Sloan all the way to LSST, we are essentially limited by point sources. We're not talking about diffuse stuff. And this is, historically, this is what astronomy has been doing. We have been obsessed by point sources of faint galaxies, in which case the flux that you receive is essentially driven by the area, the collecting area. Okay, so you maximize the size of the mirror. Now, if you look at low surface brightness, what you really want is a very fast optics, the ratio between the focal length and the diameter squared. And so this drives very fast optics with a minimal F/D ratio. Okay? And so small is beautiful. So in the context of ELTs, this is a very dangerous statement. But the beauty of the thing is that you can actually use small telescopes to do this sort of science. So you say, well, yes, perhaps Hubble can do this. Sure, but for extended objects, let's say Manning 1, extended several, almost 100 kiloparsecs, HST is just going to look just at the tip of the highest surface brightness levels. It will not see the whole gamut of surface brightness. You can also have galaxies like this one, red, dead, perhaps boring, an elliptic galaxy. You see some hints. If you go deep enough in surface brightness, then what you get is these sort of accretion events. You can see plumes, you can see streams, you can see umbrellas. Again, the signature of accretion events ongoing in this elliptical galaxy. And this is just a question of going deep in surface brightness, not in point sources. Likewise, you have the poster child of galaxies, M31, 3 times as large as the full moon. and this is a completely biased view of M31. The actual M31 is like this. And this is a survey that we did at CFHT, and you can see that the inner halo and the thick disk are extremely extended. This is essentially 150 kiloparsecs, the visual radius of M31. And you can see streams extending 120 kiloparsecs around M31. You see all sorts of features. You see all sorts of globular clusters around the streams. You can see the S shape around M33. Again, very low surface brightness. But the point is that the high surface brightness that you can see in normal galaxies, in normal images, are a completely biased view of what actual galaxies look like. If you say, well, perhaps those are huge galaxies, what about dwarf galaxies? Well, these are two dwarf galaxies, and when you look at diffuse light, as opposed to resolved star counts, what you see is that galaxies have no edges. You don't see where the galaxies stop. So the point is perhaps galaxies just they trail off in intergalactic space. We don't see any sharp cutoff anywhere. So where do galaxies stop? We don't really know. Again, this is not new. Mark Disney made the point back in the 70s that galaxies are just like icebergs, and what you see above the sky background has nothing to do with what happens below. So this is much like cosmology these days. We know the baryons, and we want to understand what is below the waterline. So galaxies are exactly the same thing. So if you look at the normal sky, this is a normal picture, you will say, yes, the sky is dark. Well, not quite, because if you go down in surface brightness, you're going to see this effect I'm going to talk, that galaxies are actually so extended that eventually there's no single patch on the sky which is not full of light. So this changed completely the picture that we have of detecting galaxies. This is an amazing image of the Virgo cluster using a Schmidt telescope by Chris Michels. The problem with this is that it is limited by systematic errors. First, you have the sky, which is changing on scales of minutes, hours, and different positions. You have straight light contamination, like here. You have light here that will go into the field of view. You also have problems with the flat fielding. You don't know whether you have over-subtracted here and under-subtracted here, because the scales are so large, and you cannot really control the accuracy of the flat fielding. And then you have to mask out all the stars, because they have extended PSF wings, and they will prevent you from actually measuring the surface brightness in these areas. So the only way is actually to design an instrument that will actually limit all the systematics. Now, we've been trying to do the same thing with different telescopes, and this is a stream detected by David back in 2008, 11 hours with amateur instrumentation. This is the best we can get with Sloan, and this is the best we can get with CFHT. So what? CFHT cannot do as well as an amateur? Yes, because we're limited again by systematics, and the systematics come from the extended PSF. You see, this is the image at CFHT, huge PSF, actually as large as the galaxy itself, and this is what a Bulgarian amateur is doing after 21 hours. Now, this image is far better than one at CFHT. Look at the PSF, how compact it is. So if I want to do the photometry of this umbrella, I better use this PSF than the one at CFHT. So this, we'll come back in a minute, comes from the internal reflections in the lenses at the prime focus. Now, the state of the art at the moment is using this camera, the Dragonfly Array. This is an old picture, but essentially those are telephoto lenses from Canon, and Bob made sure that there are special coatings to avoid internal reflections. And with this very modest array, they have made a number of discoveries which are really stunning. As a look at COMA, they detected the first 50 or so galaxies which are extremely diffuse, faint, and yet extremely large. If you look at the size versus central surface brightness, you see normal galaxies like Sloan or the Milky Way. You see the normal dwarfs spanning a large range in surface brightness, and then you see this new class of galaxies which are as large as the Milky Way, but something like 5 to 6 magnitudes fainter in surface brightness. Now, these guys, of course, have been followed up with HST, and those are nearby enough that you can actually resolve them into stars with HST. But you will be hard-pressed to detect these things with HST. HST has not been designed to look at diffuse objects, but actually resolve star counts. And again, this is COMA, and this is HST. If you go beyond that, you will not be able to resolve these type of populations. Now, thanks to HST, they could confirm that indeed the tip of the red giant branch is something like 7 megaparsec, and therefore these galaxies do belong to COMA. They are not along the line of sight. Now, looking at archival data in Subaru, they detected all these galaxies which were there, but they were not actually extracted properly. And Nature here has been doing a superb work with GTC, extending the range of surface brightness all the way to something like 31.5 on scales of 10 arcseconds. This is absolutely stunning, but of course you're not going to be able to use a large telescope to do a systematic survey of the sky. So these galaxies are found everywhere, in clusters, but also in filaments, and this is really a new class of galaxies, which is probably dominating the luminosity function. I will come back to that in a minute. This is an image of the Antlia cluster, exposed 150 hours by an amateur, and here the number of galaxies which are unknown overcomes the galaxies which were in the catalogs. So there's so much stuff actually to be detected. These new galaxies, are detected by amateurs and not by professionals. The second driving science case is the cosmic web. As you can see, all these galaxies are falling into the potential waves of Milky Way galaxies. Those are the orbits, and this is the visual radius. And the accretion is highly anisotropic, and this is the thing that we also want to detect. Not only the galaxies in falling, but actually the filaments where they come from. And so this is driving case number 2 for MESSIER. We want to detect the cosmic web. Now, this has been attempted in Oxford 6 in emission, but this is a collision ionized line, therefore the emissivity will go like the square of the density, and you will see just the very dense clumps on scales of something like 0.5 megaparsec or so. But if we believe simulations, they tell us that Lyman-alpha will be stronger by 3 orders of magnitude with respect to anything else that you can see in metal lines. Makes sense, right? Now, to detect Lyman-alpha, we can look at low redshift, and for 3 main reasons. First, the filaments will be much stronger. Second, you minimize the cosmological dimming, like 1 plus z to the 4th power. And then also we have efficient UV detectors of new generation. So once we detect Lyman-alpha at low redshift, then we can follow up at other emission lines. Now, this has been again attempted. Michael Rush was the first one to do that at VLT. After something like 100 hours, he detected all these Lyman-alpha emitters, which you cannot see the continuum, you just see the strong Lyman-alpha line. Again, it is not a very efficient use of the telescope. If you have access to Keck, like Chuck's tidal, he spent 1,000 hours on something like 100 galaxies, and he found that the UV continuum is far more compact than the Lyman-alpha halo of these galaxies. Again, cosmological dimming is a killer at this redshift, but you see again the extended emission all the way to something like 80 kiloparsecs co-moving. Now you can use again VLT with the most efficient instrument at the moment with Muse, and you can actually see after 1 hour this diffuse Lyman-alpha emission again around very high redshift quasars. And if you look at the res frame surface brightness, it extends essentially to 0.5 megaparsec co-moving. So there is lots of stuff around galaxies and quasars, but it makes no sense to go to this high redshift. Let's look at low redshift. So what is there for the future in imaging? You can say, okay, perhaps large telescopes, and Nature's been the pioneer on this field, but again, it's not optimal. You have all sorts of lens corrector. We'll come back to in a minute. If you can measure the PSF, that's fantastic, but of course you also have high pressure. So it is very nice to do targeted surveys, but not a very extended sky survey. Small telescopes like a super Dragonfly or the Huntsman in Australia, it is very cheap, but of course you have very low efficiency due to weather and the moon and so on. So it makes sense, and this is the next generation of Dragonfly arrays. Bob is going to build several of those, and so it's going to be a very efficient in the optical, but due to these limitations, due to weather and the moon and so on, it's not going to be fully efficient. And so obviously we want to find the limits. The sky is the limit, and because of this variability, we have these PSF wings due to the scattering of the atmosphere. Okay, we're forgetting that if the sky is blue, it is also a problem at night, because the PSF will also be extended just by the scattering of molecules. So it makes sense to go to space to avoid this extended PSF. Then you have all sorts of stellar contamination, even though you can minimize that. And then you have all these limits to the flat field accuracy you can make. So the solution, of course, is going to space with an optical design which will just minimize all these fundamental limits. So what are the top-level requirements that we need for this instrument? Well, we need, first of all, a large field of view, because the lifetime will be short. We need a very fast optical ratio, as I've argued, and f/2 will be 2 orders of magnitude better than HST. Again, in terms of surface brightness, not in terms of point sources. Okay, don't get me wrong. I'm going to argue that because we want PSF as compact as possible, essentially the Airy function, we have no obscuration, and these 3 requirements are quite difficult to meet together. We need something like 1 arcsecond per pixel to match what we get from the ground, and because we want to go to the UV for Lyman-alpha, so we have some requirements for the roughness of the mirrors. But the key thing is the flat fielding. Now, you can do all sorts of strategies for that, but the best one is to do drift scanning, in the sense that you're reading the columns of the CCD at the same time as your field of view is moving. And in this way, you're just improving the flat field accuracy by the square number of pixels, and essentially you reach these sort of levels that you require. Now, all these are just constrained in the direction of drift scanning. We are limited by the platform, actually, for the price. If you give me $1 billion, we can do that with a 2-meter class telescope, but that's perhaps a bit too hard to find. And we also want to do the whole sky because it will be a unique survey. So you say, okay, but ground-based telescopes would certainly do much better. Well, not quite. If you look at LSST, again, the optical elements here will produce a number of internal reflections which will be just a disaster for loss of surface brightness. For galaxies, it's absolutely fine. You see, the quality is exquisite even at the edges of the field of view. So again, don't get me wrong. It's just for the loss of surface brightness, all the scattering internal to the correctors. And this is an example of the PSF at CFHT, and you see all sorts of effects from one side to the other field of view. Again, this is the Pleiades. If you just want to do photometry of point sources, that's not an issue. If you want to measure the photometry of diffuse object, it is a major concern. For instance, this galaxy here, and this is the PSF. So it is almost pointless and hopeless to do that. Pierre Alain has been trying to do that with very carefully, but it's really, really hard. So as opposed to the nice Airy function for an unobstructed telescope, LSST PSF will be not only very extended, but also anisotropic. And so the strategies to do the proper deconvolution are going to be extremely difficult. So I'm very skeptical that LSST or these sort of instruments will be very good for that. So we have been exploring a number of different designs for fast and wide field. And we have done all sorts of studies, including some things that are not yet very well known. And eventually, we have found one solution. Now, we have to remember that we have 2 constraints. One is that we cannot use any lenses. And the reason is that if you have a very fast optics, you will be producing Cherenkov radiation. All the protons and electrons that will go faster than light within the lens will produce this Cherenkov. Usually, if you have FOD of 8, you will not see that. But you have very fast beam, and therefore you will get all the photons, the blue photons that you can see in the nuclear reactors, producing this high background. And the second requirement was, of course, a flat focal plane for CCDs. And so we got this solution with free-form mirrors, unobscure, off-axis, and the only problem is that manufacturing these free-form mirrors is very expensive. So this was one of the criticisms that ESA pointed out. We knew that, and also the problem of actually refocusing the M2 because of these very fast optics. So we published this a number of years ago, but we didn't get the funding for actually producing a prototype. Now, 3 months ago, we had a breakthrough, and we thought about a purely reflective Schmidt telescope, only with mirrors, no lenses. Now, the price to pay is that the focal plane will be curved. But we know how to do curved CCDs or even CMOS these days. And this is extremely elegant solution because then we only have aspherical mirrors and plane mirrors. And so this is the thing that hopefully will be funded next month as a prototype. Now you will say curved CCDs. Well, this is actually has been done by the military in the US. This is the Space Surveillance Telescope, a huge telescope to actually look at debris at the geosynchronous orbit. And so this is absolutely unique, but it has a huge obscuration, but that's fine because they want 2-point sources. And we don't have this sort of money in astronomy. So let's do that in a small version. Now, why I am obsessed about the PSF is that if you look at the extended area of the PSF on a space of 5 minutes, then all sorts of effects like the correctors, the filters, will produce features. And if you want to deconvolve properly, you need to assess and measure the PSF properly. And this was done in a spectacular way at GTC, and you can see the anisotropic PSF with even tangential features that you didn't expect. Again, on scales of several minutes. Usually when you do point sources, you just look at the core of PSF, and you just disregard what is happening in the wings. Now, the second effect that we want to find, of course, is the sky. The sky, this is the sky of Parnell in real time. You can see the time is changing very, very quickly, both in the red but also in the blue bands. It's extremely difficult to actually control the quality of the sky in real time, unless you're doing brief scanning, just like Sloan did. So going into space, you will gain something like 2 to 3 magnitude in the Z band, something like 1.5 in the V band, and then, of course, a huge discovery space in the UV, where the zodiacal light reaches a minimum. So this is O'Connell, and this is just the new version. This is the sky, say, a Parnell, very dark one. You have the zodiacal light, like this way. The Earthshine you can minimize because it's essentially geocoronal lines, Lyman-alpha and oxygen 2. And so you have a sweet spot around 200 nanometers where you are not really contaminated by this geocoronal emission. And then you have a set of filters in the optical to characterize the star populations in these dwarf galaxies. And we need Lyman-alpha at 200 nanometers to detect the cosmic web. So we're just following the surface brightness all the way from essentially 150 to 1,000 nanometers. So with the broadband, again, we characterize the star populations, and this is an order of magnitude better than Sloan, and better than galaxies, again, by an order of magnitude. And these two filters in Lyman-alpha, narrow and broadband, will allow us to do this intensity mapping in Lyman-alpha. Now, okay, what about UV detectors? CCDs are fine, but in the UV, the breakthrough came from GPL and Columbia, where they can do this delta doping in CCDs and reach quantum efficiencies essentially near 80% at 200 nanometers. So it's time to come back to the UV domain, which has been neglected for so many years, because now we have detectors as efficient as in the optical. Now, if you compare the PSFs of galaxies as opposed to MESSIER in blue, we just have an order of magnitude improvement in resolution and also in compactness of the design. It has been designed for that. And if you look at the PSF from Dragonfly, it will be again something like 5 magnitudes better, and essentially because we are just fighting the atmospheric scattering. So this is the idea of the focal plane of MESSIER. You have essentially divided the focal plane into 12 different controllers, and so the quantum efficiency of each CCD is optimized for each filter. And so at the end, we get something like more than 85% throughput. And it is highly efficient because there are no moving parts, okay? And it is also passive cooling. So as the galaxy is going through, you're just reading the columns of the CCD through drift scanning. So this is old, it is well known from Earth-looking satellites. And so with this sort of design, we've done a pipeline and look at, say, the actual M31 after something like 10 megaseconds, and indeed we reach something like 32 to 34 magnitudes per second on scales of 1 arcsecond. This is again undoable from the ground. In Lyman-alpha, in the UV, yes, we see the blobs of Lyman-alpha, but also the filaments of the cosmic web. It has been designed for this. And these are simulations using the throughputs from MESSIER. So again, on scales of dozens of megaparsecs, you will see Lyman-alpha shining as expected. Now, there's a mission by Caltech and Marseille, Fireball 2, which will be flying at the end of this year, hopefully. And after 10 to 4 seconds, they expect to find the cosmic web in Lyman-alpha. MESSIER will be at much higher signal to noise, and ISTOS was a mid-X mission which was not selected. So given the price tag will come out in a minute, MESSIER will be so efficient that will detect the cosmic web. Now, it will detect also the galaxies across the cosmic web, and we can think, okay, what about intensity mapping and the power spectrum of intensity mapping? And this is the one-dimensional power spectrum only in Lyman-alpha as traced by filaments. And you can detect the contribution from galaxies and from the intergalactic medium. Likewise, you can do the, well, this let me find, you can do also the two-dimensional power spectrum of the cosmic web at a redshift 0.7. Again, this is completely new science that no other mission can possibly do. So these are the error bars for MESSIER on scales, covering at least a factor of 5 in the multiples. So if you compare MESSIER in the UV, because we're going to 200 nanometers raised frame, it is again more than 1 order of magnitude better than anything else. SPHERE-X was a SMEX mission by Caltech, which was not selected, unfortunately. But even if it were selected, Lyman-alpha will be detected by MESSIER with much better quality. So to mapping the whole sky, we use a low Earth Sun sequence orbit. So we can do a full sky survey in 6 months. The key thing is actually to do the inertial drift scanning centered at the Sun, not at the Earth. In which case, after one scan you get this. After 2 orbits you get a slight shift due to the flattening of the Earth. And after many orbits, you're essentially mapping the whole sky. It means also because we're reading all the pixels of all the CCDs all the time, the throughput is massive, and so you have to have the antennas pointing to Earth continuously. Which also implies that one of the sides will be pointing to the Sun, and this one will go into the zenith direction continuously. We can detect all the things, but I mean, this sort of orbit is well known. So after 6 months, taking into account the moon and so on, you have to avoid, and the South Atlantic anomaly, you can actually get the whole sky, and of course oversampling the ecliptic poles. So you have a very dense sampling at the poles, a bit less at the ecliptic, but after 5 years of the mission, you get the whole sky exquisitely. There are some issues about the thermal analysis because one of the sides will be facing the Sun continuously, but we have done all the thermal analysis of the mirrors and so on, and you can do that with passive cooling. So there are essentially 2 critical issues. One is the focusing of the M2 mirror, another one is the straight light contamination. And for this, we design a pop-up baffle that will just open once in orbit to minimize any straight light that will, again, increase the surface brightness as the detectors here. So the beauty about this mission is that not only we solve the problem of how many galaxies are there or normal galaxies, and we solve whether the cosmic web exists, but also you have 3 byproducts because you get the whole sky in these 6 bands. So we go all the way from the solar system, comet tails, the dust and so on, to stellar physics. And I can spend hours in each of these science cases, so I'm going to go rather quickly and select a few of them only. So for instance, mass loss in giant stars, those are the episodes that are enriching the interstellar medium in metals, and this has been detected in low surface brightness in both by Akari and GALEX. You can also do time domain stellar astronomy simultaneously from the UV to the optical. You can also do the cirrus and for the properties of those grains through scattering. In the stargalactic science, of course, you do what is the actual luminosity function of galaxies, things which are extremely new, like the warm molecular content of these galaxies, and of course the intracluster light in clusters. And you can also do, of course, cosmology. I'm particularly keen on the fluctuations of the optical UV background radiation, but you can also do a new calibration of the cosmological distance ladder with surface brightness fluctuations, the Tonry method. You can do also BAOs with Lyman-alpha galaxies in this redshift range. And of course, you can do time domain cosmology. Again, this mission has not been designed for these science cases, but this comes for free. Okay, so you can exploit these maps. So let me just mention 2 or 3 issues. Science case, collateral science case number 1, what is the actual luminosity function of galaxies? If you look at the surface brightness of a galaxy as a function of size, depending on the amplitude of the sky level, it will appear that galaxies which are low surface brightness will appear fainter than galaxies of the high surface brightness of the same luminosity. And likewise, galaxies which are low surface brightness will appear smaller than galaxies of high surface brightness of the same size, just because you are cutting through an isophote to the sky. This is well known. If you look at surface brightness versus magnitude, you see that at given a magnitude, you have a range of surface brightnesses which are not accessible. I mean, you may have large galaxies which are missed, and of course you also have lots of galaxies which are missing due to the cutoff in surface brightness, and likewise in size. So extended faint objects are just undetectable. If you look at Sloan, for instance, if you look at the completeness as a function of surface brightness, here you're limited by cosmic variance, here you're limited because the instrument is not efficient. And therefore, what happens in this whole range, across a whole range of magnitude at low surface brightness is completely unknown. We don't know how many galaxies are hiding in this area. Now, the most accurate redshift survey so far is was carried out by Maret Geller a while ago. And this is extremely modest by today's standards, only 500 galaxies. But this survey is complete in surface brightness down to 22.5, which is extremely bright for our standards. And what she showed is that the luminosity function at something like -15 is completely dominated by low surface brightness galaxies. And actually the slope is entirely different from the high surface brightness galaxies. If you look at the slopes, the overall sample is almost the canonical -1.3. The high surface brightness is very shallow, and the low surface brightness is extremely steep, close to -1.7. And again, this is very, very bright. My hunch is that this point will move to -2 if we go deep enough. Now, -2, of course, the luminosity function will diverge. But -2 is also the slope of the mass function of CDM. So my hunch is that all these feedback mechanisms that we're invoking to match the luminosity function to the mass function of CDM is just bogus, because this point will move somewhere here. So this is an important issue, and Margaret was very frustrated because incompleteness is extremely serious, and we cannot deal with that unless we do this sort of surveys. Another case I'm really keen is the fluctuations of the UV-optical background, and I remind you that this is just the integral of luminosity density across all redshifts that you're measuring. And whereas it has been detected from the gamma ray to the radio domain, especially also in the infrared domain, the optical UV is a big question mark. Now, this is what we expect from simulations, that the amplitude will be as large as the cosmic infrared background, and all these points are actually not that well constrained, and this is exactly the range that MESSIER will cover. There are indirect ways to measure that through gamma rays from lasers, but it is very indirect, and MESSIER will detect that directly. And not only the amplitude, but also the fluctuations. Another case that we can do is, of course, baryonic acoustic oscillations, and those biases can be mitigated by having different traces, not only these red elliptic galaxies, but here Lyman-alpha emitters in a very thin shell. This is a wonderful window function, because it's essentially a flat one in a very narrow range at that redshift. And this is a simulation done for the expected signal in BAO, only using 3 million galaxies detected by MESSIER. So we don't need any additional science and any additional time for this. Something that also comes from free due to the strategy is time domain cosmology. We get this follow-up of gamma ray bursts, which are even brighter in the UV. But you can also do supernovae, and this is absolutely key, because we will be measuring the UV rest frame luminosity function of supernovae to compare with the ones at high redshift. And then new science, of course, those are the tidal disruption events, stars falling into black holes. And again, the light curves are predicted to be especially important in the UV. So in the same way as we are detecting supernovae across the many different years, exploding all over the sky, we'll be able to do the same thing for free with MESSIER. Again, this has not been designed for it, but we will get. And this is, again, new science, which is not possible with anything else. So we were in contact with 2 different industrial contractors, competing ones, actually. One was EADS, CASA in Madrid, and then Proba Kinetic from Belgium. And we have essentially 2 different platforms. This is a tiny payload. It's something like 65 kilograms and 65 watts. Those were the requirements set up by ESA. And you see that the design of the solar panels is slightly different. The sun shield is a bit different. But yet we were within the total budget of something like 120 million. And the number of scientists interested in the mission is growing. Now, unfortunately, this was not selected by ESA. And who knows why. But so we want to build up again the science case, and we want to publish a white paper sometime at the end of the year to make the case that there's so much science to be done that it has to be done given the price tag, which is really, really cheap. So I prefer to stop here so that we have plenty of time for many questions for all the science cases that I've not been dealing with. But the point to take is that this is a strong heritage that comes from the ESA missions or the NASA missions. This was submitted as a China Europe mission, and the Chinese were very efficient because they can actually build these mirrors very cheaply, although they cannot really do the polishing. The point is that this is a fully unexplored niche, perhaps the last one that remains to be explored in parameter space, and therefore the discovery potential of this is absolutely unprecedented. And as you can see, even though the mission has been designed to look at the small galaxies in normal halos all the way to the cosmic web, the returns go from stellar physics to cosmology in rather unexpected ways. And at the very end, this will be also a huge legacy, because that will be the optical UV photometric catalog that we've always been dreaming of, the whole sky and across wavelengths. So if you think this sort of science is interesting for you, you are most welcome to join us in this adventure. Thank you.
Thank you very much, David, for this very interesting talk. Question, comments for David?
What is the source of the Lyman-alpha photons that you expect to detect in the cosmic web?
This is just recombination. If you look at the thermal distribution of the cosmic web, you have a whole range from 10 to the 6 all the way to 10 to the 4. So at 10 to the 6 you will be soft X-rays, at 10 to the 5 you will be the hard UV, and then at 10 to the 4 you will get essentially recombinations from Lyman-alpha. Okay, so it's a well-known process given this whole range of temperatures. So that's why, I mean, it makes sense to look at oxygen 6, because it's highly ionized, probing more than 10 to the 5 degrees gas. But my point is that these are very dense clumps, okay, not the filaments themselves on large scales. So it makes sense to have Lyman-alpha. Now, different simulations will predict different amplitudes for the Lyman-alpha emission. And so I've been working with 3 different groups in these simulations, and the range of predictions changed by a factor of 3 or 4. Okay. And so there are also issues on whether, some of the simulations do take into account radiative transfer effects in the simulation themselves, or put the radiative transfer effect after the simulation. And so there are different techniques and different predictions. Means that even the amplitude of the effect of the emissivity in Lyman-alpha as a function of redshift will depend on the sort of simulation that you have. So it's also another test of these hydrodynamical with radiative transfer simulations that they've done. Okay.
Question here. So I was curious about you said that one of the topics you could cover with this, even though the project is not meant for it, was surface brightness fluctuations.
Yes.
So could you elaborate a bit on that?
Right. I don't think I have many slides on this, but the idea is to extend the technique that Tonry pioneered, looking at surface brightness fluctuations at even fainter levels. And because you also have from the UV to the essentially near infrared, you can actually control the sort of populations are giving. Because so far the surface brightness fluctuations have been done, say, with HST, Virgo, Chroma, and so on. The papers by Blackley and May and so on. But my concern is whether you're looking at the UV or the infrared that will produce different amplitudes, because the effective number of stars per pixel will be different. And so all the systematics can be covered through this multi-wavelength in these different filters from MESSIER.
But don't you need the special resolution for this? Because the fluctuation, I mean, we're used to seeing this on HST images on the scale of a pixel, but sure. Your pixels here are 1 arcsecond wide. So
that's right. I mean, it's not ideal. So that's why it's not a driving science case. 1 arcsecond is produced by the size of the CCDs that we can deal with. I would love to have smaller pixels, but then we're going to military-grade CCDs, and they're far more expensive. Okay, but I agree it is borderline. But 1 arcsecond pixels on the outskirts of galaxies will just produce the fluctuation that you wish. At the centers, it will be more difficult. I fully agree. Okay, and actually, we need to actually make quantitative predictions of the SB fluctuations for this MESSIER case, and I think Miguel is going to work on this with Simon May.
Yeah. Thank you.
So it's 1 arcsecond pixel, but what's the PSF in the UV and
Right, I showed the PSF compared with Galaxy and Dragonfly, and it is correct that with 1 arcsecond sampling, you are undersampling the core of the PSF.
Right.
Okay, so for point source photometry is going to be an issue.
However, in the red part of the spectrum, would you sample correctly the PSF?
Yes, yes. I mean,
And may I ask then what's the expected sensitivity after the survey is performed?
So after
for point sources.
For point sources, the sort of red band filter, we go down to 25 magnitudes in 1 year.
That's great. So I guess it's a couple of hours seconds then, PSF.
The effective size, yes.
And then you are getting to 25th magnitude?
Yeah, that's right.
That's comparable to Euclid.
Sure.
You realize that, yeah?
I know. Actually, I argue that we can provide for free the photometric redshift that Euclid requires.
Yeah, so that's very interesting. How many sky coverage, how many times you pass across the full sky?
So the full sky is covered in 6 months. Okay.
And then if every 6 months you have a full sky coverage?
No, but you see the coverage is different depending on the ecliptic latitude. At the poles, we will be sampling every 90 minutes. So we have high redundancy. In the equator, it will only be a few hours, okay, every 6 months. Now, we have to be careful because the PSF is not the only thing. Because it is 1 arcsecond wide, we will be contaminated by dwarf galaxies at magnitude about 23, 24th, okay? And will not be able to disentangle dwarf galaxies, compact galaxies from stars. So for this, we have 2 mitigations. One is used as a prior for the astrometry, the Gaia catalog, down to 21. Now, to 21 to 25 is another gap that we don't know. But then we can think about the Euclid fields, okay? And whatever they are, we can use that as a prior for the astrometry and then disentangle stars from dwarf galaxies. So one has to be careful. I mean, I'm not sure it will be as faint as that, as 25, even more after 5 years if the mission is that faint, okay? Because of this disentangling issue with contamination. But still, it will be the first UV catalog from the UV to the near infrared in space. And we can mitigate many of these effects.
David, thank you for your presentation. Is there a way that you could possibly make the same kind of science, or not so challenging, but with a smaller satellite? I mean,
even smaller?
Yes. Much smaller. I mean, in the range of nano to CubeSat sizes. Yeah. Just to start with, and then to just like...
Yes. Yes, it will be much cheaper. But the problem is, and actually there are 2 projects which are competing with MESSIER in this. One is Australian Space Eye, which is a 3U CubeSat. Another one is Dune, done by Guzman in Florida, which is, I think it's 25 centimeters in diameter. The problem with these 2 designs, which are much cheaper than MESSIER and much smaller, is that they use lenses, and therefore they are going to be killed by the Cherenkov. So I've done the simulations for the Australian Space Eye, and they want to mitigate that by looking at the red filters, not the blue ones. Of course, Cherenkov goes like 1 over lambda, so it makes sense to go to the red, but still they will still be contaminated by there. In the case of Dune, the optical design is patented. I cannot have access to it, so I can predict what the Cherenkov background will be. So if you can think of a purely reflective design, okay, no lenses whatsoever, then of course CubeSats make absolutely sense. And so we can try to convince the Australian friends to change their design and use mirrors. But then that will not be a 3U, it will be perhaps 6U, and it starts having a price tag which is higher. The other problem for these CubeSats is the orbit. We still need something like a polar orbit, and there are few launchers that were able to do that. So there are a number of issues that make this solution less attractive. But you're right. I mean, if we not get funding for this mission, let's go for a smaller mission by all means. But again, even the attitude control of the CubeSats and the sampling, there are so many issues that I think this is cheap enough, which is worth the effort, you see. Cheaper is not, faster is not necessarily better in this context.
Hello. It sounds to me like there is a huge challenge in analyzing the data with respect to classical galaxy surveys. you will have to run a huge parameter space in simulations to understand what's going on. And what kind of biases do you expect in the cosmic web, like saturation and like the peaks not so well, the density peaks not so well resolved or something like that? I don't know. What kind of biases?
Well, saturation is not really an issue because you have drift scanning. So the individual exposure time is very, very short, a few milliseconds. So what you're actually doing is integrating many of them. So I think saturation level that we computed for the CCDs was something like 8th magnitude. Okay, so you don't expect any of the signal there. On the contrary, we just have so many photons in this regime. On this question of the clumps in cosmic web, again, we're not designing this to high-resolution clumps. We're just looking at the diffuse emission. Okay, and so you can do all sorts of filtering to actually detect large-scale features. Okay, now you can always do follow-up studies in other lines to look at the very dense clumps if you're interested in that. Now, a more serious issue is the one from the foregrounds. Okay, I thought you were going to ask about this. Because, of course, you have diffuse emission from the scattering of dust grains around nearby stars. And this, I think I do have, you can see that in the UV, those are dust grains around nearby stars, which are just scattering the light off the star. And, you know, those are the galaxy fields 1 degree in diameter, and they are everywhere. And if you look at Nacho's pictures, or David, Martinez Delgado, they are everywhere. In fact, we did a power spectrum analysis of the series using Planck, using WISE, and using CFHT, and you see you have a beautiful Kolmogorov cascade all the way to a few arcseconds. And this is the main challenge, if you want, because we have just a strong foreground. Now, we can use the same techniques as in the CMB, right? Except the CMB is very easy because they know what the background is. Flag baud at 3K. In our case, we don't know what is the spectral energy distribution of the sources, but we know the spectral energy distribution of the dust grains. So we can do some sort of independent component analysis and remove the foregrounds in order to detect what the background source is. Okay. So looking at the cosmic web or looking at fluctuations of the EBL, this is going to be the main limiting factor, okay, as a systematic. And if you actually extrapolate, we find that essentially less than 30% of the sky will be free of this contamination at levels of something like 30 magnitudes per square second. So this is the most serious concern, but we're dealing with that with simulated images, and we are using different techniques to actually remove these foregrounds.
Any more questions, comments?
What's the motivation for the redshift of Lyman-alpha?
Okay, so it's a double motivation. Okay, one is going to low redshift because the cosmological dimming will be smaller, because the cosmic web will be more intense, and then because we have the UV detectors. Okay, as you know, this has been attempted from the ground. For instance, you have the Cosmic Web Imager at Keck by Chris Martin, and they're looking in the optical regime at redshift 2.5, something like that. So you have at least an order of magnitude, if not 2 orders of magnitude fainter. Okay, and at redshift 2.5, the cosmic web and these filaments are much, much less intense. So it makes sense to look at the smaller redshift as possible. Not too low, because then you have the geocoronal contamination. Not too high, because then you also have the oxygen 2 geocoronal emission. So you have a sweet spot around 200 nanometers. Okay, and we do have the technology actually to do this experiment at 200 nanometers. The balloon mission that I mentioned, Fireball 2, those are going to actually use the CCDs from GPL Caltech, these delta-doped CCDs, and they're going to put that into the balloon probe and test them. They are not space qualified yet, okay? And they're looking again at 200 nanometers.
Thanks.
Of course, also the zodiacal foreground is minimum at that wavelength. If you go to a higher redshift, and therefore longer wavelength, you also have the zodiacal light, which is an issue. But this is the easiest to remove as a foreground because it is rather smooth. It does change with the solar activity. It does change with the comets going through, but it's easy to remove.
One small question. Could you go to a lower redshift? Is it possible, like 0.4 or something?
The short answer is perhaps, in the sense that if we can move the doping window into a shorter wavelength, it could be done. Do you have any idea behind that?
Yes, because the foremost survey will. One of the projects is to actually proposed was to use the VISTA observations for the imaging to then use observe bright galaxies and have like the cosmic wave with about redshifts with about 18 million objects.
Sure, sure.
And they would peak at about redshift 0.4.
Yeah, but I mean, at redshift 0.7, 0.8, you have many galaxy surveys which are reaching that depth, right? Vipers, for instance, go even fainter than that. So 0.8 is a relatively nearby universe where you can actually do a redshift survey as a follow-up.
I'm talking about 15,000 square degrees, and that would be interesting in order to cross-correlate with other surveys. So that's why.
Sure.
Like Vipers is like a beam survey. Right?
No, I would love to have a different redshift interval, so you can do actually tomography in 2 slices. But I mean, the actual redshift range is not yet defined. It will depend on the actual characterization of the CCDs. The nice thing is that the filters, because you have always problems with the red leaks, the Chinese actually can manufacture these layers on top of the CCD. You cannot afford any glass filters because, again, of Cherenkov. And so you can actually deposit these coatings on the CCDs, and you can actually tune the filter at the wavelength that you wish, even in the UV. So this is the nominal value. The actual value will depend on the specifications of the actual CCD.
Any more questions? Yeah, I have one short. As you have shown before, also we can use gamma rays coming from distant blazars to constrain the extragalactic background light. And I wonder, maybe I didn't realize if you mentioned it, what is the uncertainty that you will expect in your measurement of EVL? And also, how much fluctuation do you expect? What is the percentage? Because I think from gamma rays we are around 30% with respect to the theoretical models. So,
well, those are the expected fluctuations for the Cyber 2 experiment. You see on these small scales at something like 0.8, that's the reddest point that we're getting with Messier. We still have a contribution from the high redshift galaxies. Okay, and so to answer fully your question, the amplitude will be, this is the intra-halo light, but essentially you have contributions for the low redshift galaxies and the ones for the high redshift galaxies. But you see, this is the sort of fluctuation we expect. Okay, again, on those small scales, 3,000. I've not done, the whole point of measuring that on higher, on larger scales, but I've not actually done the calculations yet. Okay, but this is the amplitude of the power spectrum on those scales. And the interesting thing is that if you go even higher redshifts, then it moves into this band, which is not observable by Messier, but it is observable by Cyber 2, which is a rocket flight. Okay.
Okay, thank you very much. I think there are no more questions, so thanks to the speaker again. Thank you.
Thank you.
So I just have a comment. So if any one of you want to talk with David, we have now time from 12 to the lunch time, just because during the afternoon I will be working with him on my group. And then I will